Well, in this video we'll run a script about image processing. So this is not about machine learning, but many problems in machine learning involve image recognition, and so it's interesting to know how to work with images in R. And here we're using a package that comes from this website. It's called Bioconductor, and this is a place where they have free software for bioinformatics and genomics and so on. And they have one package specific for image processing, which is called EB image, and this is the package that we'll use. And they recently changed the way to load the package, but I have this update in my script. So you have to run those lines here to install this package. I think that we don't need this. And then I may load this library, and that's it. And what else? We'll create some images by yourself, but then we'll use some images. You have them in Atenea. So here in the course at the end, with all the data, you have photos and photos. So the first part is a zip file with some JPEG photos. So I have them in my folder, but you can get them from this file. And I also put two photos which are black and white for processing without bothering with color. So you can get them in the Atenea course. And so for the script, we'll start by generating images, and first by just using random numbers. So first we'll get a white noise image, and then I define the size of the image. So I just create two variables, one with the width, another with the height. And then I also need the number of channels, and since this is a monochrome image, I only need one channel. So channels refers to the number of color channels. Usually you have 3 channels, red, green, and blue. And sometimes you have a 4th channel for transparency, which is the alpha channel, or the opacity of the image. And now I put them in a vector, the 3 numbers. And now I compute the number of pixels, multiplying this, the 3 values. And next I get the data to put in the pixels, and this is just a list of numbers that will mean the intensity of light in the pixel. and I do them by using a uniform variable. Unif is the name of the uniform variable. The R is for generating, and then I pass the number of values that I need, and also I pass the dimension, so the data will be an array with the right dimensions. So in that case we use array because we think of 3 indexes, the x and y coordinates on the plane, on the image plane, and also a z, let's say, coordinate for the channels. And in that case the data structure is array. So this is similar to matrix but with more indexes. So I enter this, and next I create the image, which is some kind of object, using the command image with uppercase I, and I have to pass data, dimension, and the color mode, which in that case is grayscale. And so I define this, Control R. And next I want to look at the image. So you have two ways to do this. One is using an external display that shows in a browser, and you do this by using display. So display sends the image to a browser, the default browser, I imagine, Control R, and so in that case it opens in Firefox, and you have here the image. And the other way is to get the image in the R interface, and in that case you use display with method equal raster and all equal true. All equal true means that you want to see all the image, and here the resize is to make the image larger, just Control R, and so now you have here the image, and so it shows in a window plot as usual. And then you have this random kind of noise here in the image, and but this is just to illustrate how to create an image and then watch in a window. The print shows a bit of the pixel values. Notice that in that case pixels are float from 0 to 1. In some places, programs or so, the image is given by integer values. Usually if you are working with 8 bits for channel, the color, that gives you from 0 to 255. But now you have the values as float from 0 to 1. And the next example is similar. You define some width, some height, and now we will want 3 channels because we want to get a color image. And dimensions, number, and then an array. And now this array are normal values with parameters. The mean is 0.5 and deviation 0.15. So you are still in the interval from 0 to 1, but now the distribution has more weight in the middle part. And now to create the image is like before, data, dimension, but now the color mode is color. And it's not enough to have several channels to understand that this is color, because for example, for medical applications, you might have channels that correspond to different positions in some dimension in the space, like for some kind of scanners which are used for medical applications. So in that case, it understands that the three channels mean color. So Control R here. I think I didn't run the data line. And now I display this as raster. That means that it opens here. And so it's like before, but now the image is color. So at every pixel you get 3 color components. And here you have the print. So as before, it's just a few pixel values. And an histogram, since this is an array, the histogram is for the 3 channels. So you have a blue histogram, a red histogram, and a green histogram. So here you see the distribution for the 3 channels, which of course is similar because the generation is the same. And then you might print them, not printing, but just writing them to a file. And you do this by using Bright Image, and then you pass the image object and then the file with the extension that you want. And you may use TIFF, that has no compression, and you may use JPEG, and since it has compression, then you can specify the quality, like a typical value for good quality could be 80. And if you do this, you get files with the image. So here you have now the what's this called, the test image. So the TIFF file, that's it. Good. Make it larger. And the JPEG version, which, okay, so that's it. And okay, so that's how a bit to play with the main commands. And now we'll get images by reading files. So you need a data path. Well, it's just a name I'm giving the variable, a variable holding a string holding the path. And so you may use, depending on how you have things. Here I know the path. I look at the path for the files, and I'm just entering this. Notice the symbol using the escape symbol for the anti-slash character. So now I get images by the path of a full image by pasting, that means joining the strings, this path with the specific files I want to use. And those files come from a book, which is the Laude book, which I'm just mentioning here. But you could use any JPEG image, and usually when you are doing image processing, you need some images which are sometimes very standard, and they come from laser scanning of films, but the reason is that you want something that has no process in it because you are doing image processing. But today you have so many JPEG images that you can get that, well, you can work with this. And we are not doing really serious image processing, so it doesn't mind if they are just ordinary JPEG images. And so let's go here. So first I build the image path, and so I'm pasting, and here is the separator is the thing you put in the middle when you paste, and by default I think it puts a space, so you must put here the empty string for this, Control-R. And now I'm reading the image by using read image command with the path, full path for the image. So I think that this could be maybe an URL or other kind of addresses. And printing now gives me more information. It says that color mode is color, that it's stored as float values, double. The dimension is 3 channels and 3400 by 3400 pixels. And so this is it. And you have here a few of the pixels values. So this is for one of the channels. And if I want to get the width, I use dim, because dim gives me the dimensions of the image. Is a vector with 3 values. That is, so I'm just putting them as variables. I think I'm not using this, but in any case. And now I use display. All the displays I do from now on are in the same interface in the program. Control-R. So that's it. And this is the image. And of course now is a color image and displays like any JPEG image. So here this is just to look at the variables you have defined, I think. So here you have the different image variables we have defined. And you can see here that the images are a specific class that comes from this package we're using. And if you want an array with data, so you might just work in a geometrical way with the pixel values and having like a regular matrix. You might use image data, passing the image object, Control-R, and now you have an array, so you can see here, which is numerical and has these 3 dimensions, so it's an array, not just a matrix, and a few of the first values. So this is the structure command that we have used so many times. And when you process an image, you want to compare with the original image, usually. So here I define just something to plot the 2 images side by side, and this is a function I'm defining. So it's called IMDisplay2, because it's for 2 images. It's a function that has 2 arguments, the images you want to put. And what I do is I check that the dimensions are the same, and then I combine them in a new image. So combine, put them side by side as only one image, and then I display this larger image. So this is a very simple function. Here, maybe this is not the most convenient way to do it, but if the dimensions don't match, then you just plot the first image and ignore the second image. And so, for example, if I subtract a value to all the pixels, so here you still have the vectorization working, so you might do an operation on all pixels like this. I call IM1 to the output, Control-R, and now I display both images. And oh, sorry, I didn't run the function. Control-R, and so here you have the 2 images, and notice that the second one is darker, and this is before we lowered the values. And remember that for the color values, 0 is black and the largest value is white. In that case, we are going from 0 to 1, so 0 is black and 1 is bright. So low values are dark images and high values are very light images. And so since we subtracted a value, this has gone darker than the original image. And what else? Here I'm creating an image which is just an empty, let's say, image or all white, because it's an array with the same dimensions that my images, but just using ones. So if you put everything to 1, you get a white image. And I enter this, and I use this for this IMHC new image that I want to create. And now I put to 0 the values of this new image, so I put it to black the places where the original image has small values, like less than. So IM is the cat image, and now I'm getting a new one which is white everywhere except where the original image was less than 0.3, where now my image will be black. So what happens is that the dark parts of my original image go to black, and the light parts of my original image go to white. And the value, the border, the frontier value is 0.3. So Control R, and I plot both images, and I have now this. And the only thing is that, in fact, for the white you get white, but the black is not black always, because you have the three components, and sometimes there only survives one or two of the components. So instead of black, maybe it could be yellow or red, or you have maybe like 6 possible values, RGB, and then the combinations of two. So here you have this kind of magenta value. And of course this only happens for the dark values in the original image. So this is like a high contrast version of the image. But of course the color plays in a bit of a strange way when you do this. And you could modify this to keep the work on luminosity, but then getting only black and white. But the way we did it was just for every color component, so this is what you get. Well, more things. Now we change the image, Control R. This is called X, and I read the image. I transform it to IM1 by multiplying by 1.5, so I'm scaling the light values. Print, now you have values larger than 1, and I display both things. And what this does is to enhance to increase the contrast, because you have now a larger step in the color since you are multiplying all the values. So the middle parts get light, and I think dark parts get more or less similar, because at the end, since you are going outside the interval, there is maybe some compression at the end. So this affects more the light parts than the dark parts. And here there is another image. And now what I'm doing is doing the square. So the square in that case does the square of every value. This transforms 0, 1 to 0, 1. But when you do the square, the small values get smaller and the large values get like closer to 1. So this should affect the contrast. Here I have two different displays, I don't know why, but this is the original image. And this is the new image. So notice that the contrast is increased in that case. So dark things get darker and light things get lighter. And this sometimes is which is called gamma correction. And so this is a non-linear modification of contrast, and here you have the two put together, so you can see the effect. So it's like colors here get more intense with this transformation. Another image here, controller, defining the image, display of the image, which is this image here. The dimensions are small, 250 and 375. And now I'm getting a part of the image just by using index syntax. So here at the end I put nothing, that means that I get the 3 channels, but not for all the values that I have here, but only from 1 to 200. And I display the new image. So this is a way to get a crop of the image, a smaller part of the image. And here I use the flip and flop commands to the original image. And you can see that flip is a vertical reflection, and flop is an horizontal reflection. So flip and flop do the reversing in the X or Y directions. Here is another image, controller, display. So that's the image. And now I'm just not defining a transform image, but just displaying the transformation. And here you have translate. You can do translations to an image and then the vector translation. So this is just moving 200 pixels in both directions. So as you see, you get this translated image. So the part that was outside the image now is just black. So it's just zeros. So it fills with 0. And you can also rotate, and then you have to pass an angle here in degrees. So this is a rotation of 45 degrees. So you may do geometric transformations on images. Here is a new image. Control R. Define the image. Display the image. So this is the image now. And now I'm doing a general linear transformation, and for this I pass a matrix that has 6 components, because it's a linear transformation in the plane, which is a 2x2 matrix, but plus a translation. So it's put together the translation and the proper linear transformation. And here I transpose to plot the matrix, which is this matrix here. And then I transform the image by using the affine. Affine means affine transformation, which includes a linear matrix action plus a translation, and the second argument is the matrix for doing this. And notice that the matrix is given with 3 rows. So it's the transpose of this matrix. You may play with this to see exactly the meaning of every coefficient in the transformation, but now this is just, and now I display, let me see, okay, I haven't. So this is the effect, and of course when the outside parts of your image appear, they are zeros. So now you have translation and also rotation and the deformation of the image. And this is just dimensions, taking a part of the image and displaying this part. We have seen this before. And what else? So for this section, this crop of the image, we look at the histogram. Okay, so now is from a color photograph, is not uniform, and you have like 3 histograms. So you see this in many digital cameras, photographic cameras today, the color histograms. And so this means that red is strong in this image, and also green, but not so the blue. So the image has not much blue, but it has red and green. So let me go there. So this was the image, so it's clear that red and green are the dominant colors here. And you can modify the histogram, which means like modifying the color values with equalize. So this is an automatic way to normalize the histograms. So now the new histogram is this one. So the values get normalized, and this is the effect of normalizing. So it makes also the contrast to increase because you are pulling the values to the extremes of the interval. And here I'm applying a filter. You can apply filters, so this is a command for applying a median filter. So that means changing at every pixel the value for an average of neighboring pixels, and the size of this region is like 5. And now you get this smooth effect. So this is like a low pass filter, so you lose details and get this smooth effect. And you might wield filters by using the make brush command. I have an example here. I think that this goes to the browser, but anyway, so you have this effect here. And well, this is just another image. Here I'm using an image that's from the same package. The image is called Nuclei. And then you here display at the end the filtering of this image. So it's like this display, and after filtering you get this smoother image. And well, this is more or less all the basic commands. At the end I have an application more for illustration of singular value decomposition, and since I haven't explained this in class, I don't know if it makes sense to do this now, but since it's in the script, I'm running it anyway, and if you know something about singular values, maybe you can follow the explanation. So here I'm using a monochrome image. You have Brad and Mila in Atenea, so I'm using this one. I'm building the image, the print of the image. Notice that even if this was black and white, it's still color. So this happens because JPEG usually you get them in 3 components. Even if they are black and white, it's just that the 3 components have the same values. This is the usual thing. And here, let me see, I'm just getting the dimensions, and here I'm displaying the image. So that's the black and white image, even if now it's like working with a color image. And here I have a crop, a display of the crop. So here you may see the noise you have probably from the JPEG compression. And so what I do here is I get the X and Y dimensions, so I just do the dimensions for the array in one channel. This is one way to get this. And then I'm doing here a singular value decomposition of the image, applying SVD, which means singular value decomposition, to the image. And since I know I want to work only with a matrix, because in fact this for a black and white image is what you should have, I'm using just one component. I don't remember well why the two, but I think the three components are the same. So this is now is a matrix, and the singular value decomposition applies to matrices, and it gives you one list with two things, which are first a vector with the singular values in decreasing order, and then a U matrix and a V matrix. And what you have is that your original matrix has a decomposition multiplying some kind of diagonal matrix, but it's not a square matrix, having the singular values in the diagonal, and then U and V at every side. So it's like similar to a diagonalization, but it's a bit different because it's just for rectangular matrices, and the meaning of the values is different from the eigenvalues of a matrix. And so here I get the U part, which is a matrix, Control R. I get the V part, which is another matrix. I get the list of the vector with the singular values, and then a matrix with the singular values in the diagonal, which I call D. And here I open a double plot, although I could have used the function I did before for this. And then I have here a number, and what I'm doing is I'm reconstructing the image. So the image is U multiplied by this diagonal thing by the transpose of V. And if I use the full matrix D, this is just the full image. But what I'm doing now is just putting to zero some of the singular values and doing the reconstruction using the other values. And for visualizing, I just reconstruct by putting to zero in the diagonal part the lower values. And so int is like how many values do you want. And then what I do is B that has the values. I put to zero the complementary parts, so I'm keeping from 1 to int, and the rest are go to zero. And so, for example, let me start with 150. So the length of the vector vals, the number of is 500. So the thing is that we are doing some kind of compression or just getting the the main part of the information by reducing this. So this in big data, machine learning, is related to the idea which is called principal component analysis. That means keeping the principal components, which are the ones that correspond to the larger values in the list of singular values. So now we are having a visualization of how these things work. So, for example, remember that we had like 500, so this is a reduction in the number of the values, and then b is vals, put to 0 the smaller values, build the new diagonal matrix, reconstruct the image, and now transform this in an image and display the image. And because I put a matrix for the plots, I can see both side by side. So this is the reconstruction, and this is the at the right you have the original, and at the left you have the reconstruction. And as you can see, they look really the same. And you can repeat this by changing this value. So 100, for example. That's it. And you can start to see some noise in the reconstruction now. So still you have essentially like the same image, but some effects start appearing in the image. Let's go to 50. So this is 1/10 of all the values you had, and you can see here the effect. So you still recognize the image, but you have this noise which now is more severe. And I don't know, we can go to 20. So that's the effect. So you now start losing the image. So here maybe you recognize what you have, but not who you have. Okay, so some important information has been lost, and with five only, you get this. Okay, so still you get some information, but you lose the content of the image. But as you can see, you might extract important characteristics of the image, keeping only a very small part of the information, which is the sense that this has. So this is a way how to show how it works, the singular value decomposition for reducing components. Of course, this is different because it's working just in an image, not in a data frame. But that's it. And this is all. I have some code here, but this is, as it says, incomplete. But I thought of the problem of how to resize images by doing some kind of resampling and thinking about those ideas that because you can do this in many ways, I wasn't sure which was the most natural way to do those things, and I just forgot a bit about this, but I still have this code here, so I'm just letting it here. And so this is it for the image processing examples.